Welcome to the Alvin Anderson Award ceremony and distinguished lecture. Okay. My name is Lian Shen. I'm the director of Shanti Penprase Laboratory, and I'm very glad to see so many people here. And also, usually there are a lot of more online watching the ceremony. Okay, okay. So let me first say a few words about Professor Anderson. Professor Anderson was a native of Minnesota. He grew up in Duluth. Yeah. And he got his degrees here. And then during World War II, he worked for the government. And then after the war, then he came back. And he got his degrees here. He became a professor here. Okay. And he became lab director here. And so in 1974, he served as the director of Shanti Penprase Laboratory. And unfortunately, only after 1 year, in 1975, he passed away. And he was on a trip and to do some work for the lab. And so, yeah, okay, so that is what happened. Okay. So after he passed away, then Professor Anderson's students, former colleagues, families, they put together this award. And that has been given to a SAFL student working in hydraulics in water resource area every year. Okay. So this year, okay, we have our student winner, Shanti. Okay. And okay, next, I'm going to invite Shanti's advisor, okay, Professor Andy Wickert, to come here to say a few words about Shanti.
Thank you, Lian. That was a wonderful introduction. And as a matter of fact, Alvin Anderson was the advisor of Gary Parker, who is someone who's been a close friend of our groups. And I think Shanti might be getting to know him a little bit better when he visits the lab soon. So there'll be a direct connection. In the field that I'm in, and therefore the field that Shanti's entering, geomorphology, there have been, broadly speaking, I think, two traditions. One tradition has been to tell the history of a landscape, tell the story of how it formed, how it's evolving, how it might change into the future. And the other one, which has actually evolved quite a lot from civil and hydraulic engineering, comes from understanding the processes of sediment transport, of weathering and erosion, and destabilization and re-equilibration of a landscape. Something I think is fantastic about Shanti is that she's been able to work as a field-centered scientist, which would be traditionally telling the story of a single place, but in ways that actually allow us to test and enhance our ability to understand the processes and predict the future, right? Because whenever we're solving a set of equations, we need our initial conditions, and then we need the process itself. And actually mapping in the field provides both initial condition and data to assimilate into the model to be able to predict the future. And that becomes especially important as we see today's climate and today's land use practices changing so dramatically that we're not able to just assume that things will kind of continue on as they have in the past. Shanti's actually taken that a step further, as you'll see in her last couple of slides, where she's in fact using field data to combine different methods that were traditionally used for dating sediments to actually create rates of erosion and be able to understand those through time. And that's another important piece into understanding the future. So with that, I don't want to take any of the thunder away from what Shanti's done in the Whitewater Valley here, and it'd be great to invite her up in just a quick moment. But I think that the thing to really understand is that we have an incredibly interdisciplinary research group, and Shanti has really been the one leading the way in understanding what's happening in the field, collecting the data, working in the lab, and working, in fact, in a very interdisciplinary way, from essentially from engineers all the way to people like Jimmy in the audience working on historical records to understand what happened in this landscape and create better capacity to predict landscape futures. So thank you, Shanti.
All right. Great. Thanks, Andy. Yeah, I'm really glad to talk about some of my work today very briefly. And I'm really honored to receive this award. It's been really great being in the Earth Science Department, but also at St. Anthony Falls Lab, having those two communities that I can be a part of as a grad student that's just trying to figure out what's out there for the next phase of my career. So I'm going to be talking about a little bit of the PhD work that I've been doing here at the U of M. Specifically, I'm going to be talking about a project I've been working on, thinking about the impacts of glacially driven base level change on river channel lung profile, how this varies across timescales. And I'm going to be focusing on my field area, which is the Whitewater River Valley, which is in southeastern Minnesota. And this is a picture of the Whitewater River Valley with some folks out there when we were doing field work a couple summers ago. I think, okay, cool. All right, so as many of you may know and maybe don't know, Minnesota's landscapes have been shaped by glaciation. So the Laurentide ice sheet covered much of northern North America at the last glacial maximum, which was about 20,000 years ago. And the impacts of the Laurentide ice sheet are still very much felt in the Minnesota landscapes we see and know today. So this is a map showing a reconstruction of the Laurentide ice sheet margins here in these gray colors, and my field area, which is the Whitewater River watershed. You'll see the Whitewater is a tributary of the Mississippi River. And just for reference, where we're sitting here in the Twin Cities is kind of right up here in this little bend in the Mississippi River. And what we can see just looking at this map is not only was much of Minnesota covered by the Laurentide ice sheet, but the modern Mississippi River was directly connected to the Laurentide ice sheet and the Paleo Mississippi River as well. So as a proglacial river the Mississippi River was very much impacted by changes in the Laurentide ice sheet. So as the ice sheet was advancing and retreating, we were getting a lot of changes in water and sediment supply, which many of you guys think about, and that dramatically impacted the bed elevation of the Mississippi River. And also, not only were there impacts directly on river systems connected to the ice sheet, a lot of the landscape around Minnesota is considered today periglacial or recovering from the impacts of glaciation. And so a lot of the questions that I'm thinking about with my field area are the impacts of this periglacial change, or the impacts caused by the ice sheet being close to the ice sheet, but not directly implemented by the ice sheet. So as I mentioned, the Mississippi River was directly impacted by the Laurentide ice sheet. So this is a plot showing just that. So we have age in thousands of years here on the bottom. This is the modern day, and this is about 30,000 years ago. And we have Mississippi River bed elevation relative to the present. And the main points that I want you to take away from this plot are that the bed elevation changed a lot. And the main periods that we sort of think about as we talk about this, and in my talk, what I'm going to be talking about is what I'm calling this ancient time period, where the Mississippi River was greatly incised below where it is today, was actually thought to be flowing on bedrock. Then there was a period of ice advance that caused the river to very rapidly aggrade and create a new floodplain level that we call regionally the Savannah Terrace level. Then there was a period of incision that abandoned that Savannah level and created what we call the Bagley level regionally. And then another period of incision around about 13,000 years ago, and since then gradual reaggradation. So in my work and in this project, I'm sort of framing this in these three time periods. We have this ancient time period where the river is flowing on bedrock, this last glacial maximum period where the Mississippi River was occupying these two terrace levels, and then of course the modern where the river is today. So as I mentioned, the Whitewater River is a tributary of the Mississippi River. And the big guiding question of this part of my work is thinking about what were the impacts of glacial cycling on river systems not directly connected to the ice front. And a lot of what I've been talking about is this term base level, or the water level at the mouth of the river. So that plot that I was showing about the Mississippi River is directly related to the base level of the Whitewater River. So the Mississippi is setting the base level for the Whitewater. And so those impacts of the Laurentide ice sheet on the Mississippi are having direct effects on the Whitewater River. Great, so I'm gonna jump in with the modern system here. So the modern Whitewater River, this is just showing the channel network. We can see the Mississippi River is here. This color grade on the channel network is just showing elevation, with high elevations being blue and lower elevations being red. But if we look at the modern channel lung profile of the Whitewater, we can see these impacts of this base level change. So this is the channel lung profile of the Whitewater River. The channel lung profile is just the slope of the river. So if we were looking at the river from its side, these are the slopes we would see. And for reference, this upstream portion corresponds to these sort of more blue colors here. And this downstream portion here is that confluence with the Mississippi River. And when we look at this channel lung profile, we have elevation here on this left column and down channel distance here. Also, this color grade on here is showing the depth to bedrock. So we also notice as we kind of get more in that upstream region, we have very shallow depth to bedrock, bedrock at the surface. And then as we get more downstream, we have very thick depth to bedrock, greater than 50 meters depth to bedrock. And so what we can see is we look at this channel lung profile is we see preserved today in the modern river channel lung profile this nick zone. And these nick zones are formed by changes in base level. So this is just a schematic I've drawn here. And we can see if we have this change in base level, if the base level drops, that will cause the river to sort of have to accommodate that new level. And that creates what we know as a nick point, and that will propagate upstream. And so what we can say today, just looking at the modern river, is that there are dramatic impacts of base level change that are still preserved and being sort of processed by this landscape today. And so that is sort of our thinking about the modern system. But then let's think a little bit like, how has glaciation impacted this river system over time? So I'm going to take our time machine and go back in time a little bit. And we're going to jump into this last glacial maximum period that I was talking about. And that was a period of terrace formation. And this is a plot or a picture from Google Earth, just showing how many terraces there are on the Whitewater River. So this is looking upstream. We have the Mississippi River to our back, and you can see all along here, we have these terraces that are preserved right at the mouth of the Whitewater River. And so even today, there's a lot of this sort of record of previous floodplains that are preserved in this whitewater landscape. So what we did to kind of to constrain this last glacial maximum time period, I went in and I mapped each of these terrace levels. And so this is part of my map that I made. This red line here is the valley center line. And then this color grade on these little terrace polygons is just showing the terrace elevation, with darker colors showing higher elevation and lighter colors showing lower elevation. And so we can see that there's a lot of terraces sort of near this mouth of the Whitewater River. We also took a number of geochronologic samples, and I'm just going to be showing a subset of those today, but we also have some others that we're hoping to process. But we used optically stimulated luminescence dating to try and get ages on some of these terrace surfaces that we're looking at. And so what we did to try and understand the channel lung profile story for this time period is we took these terraces, we linked them to this valley center line, and we were able to reconstruct a channel lung profile, comparing it to the modern valley center line that we see versus all of these terraces, and kind of interpolate what the channel lung profile could have looked like when these terraces were the active floodplain. And that's what I'm showing here. So we have this modern valley center line here shown in black. Each of these blue dots are one of these terrace polygons that I mapped. And then we have two sort of preliminary interpretations of what we think the channel lung profile could have looked like when the river was occupying those surfaces. You'll notice that we've got some ages on here as well. These ages are a little bit more complicated. I won't get into the nitty-gritty in this rather short talk, but it's kind of interesting. We have these slackwater deposits that are actually here and are younger than some of our lower terrace surfaces. And that's kind of an interesting story that I have an undergraduate that I'm working with in the Eastside department look at. We think that there was a period of basically lacustrine time or setting at the mouth of the Whitewater River. And so we're trying to understand how we can get sediments this young on top of this terrace surface. And then we also have some other dates here that are from tributary terraces. So we can see not only is there sort of a complicated story with the slackwater, but there's also a complicated story of propagation of this nick point upstream. And so, yeah, so this is what we're seeing as we sort of reconstruct this last glacial maximum time period. And what we can say is that terraces preserved in the modern Whitewater River record several periods of incision triggered by glacially driven base level fall. Finally, let's jump into the ancient time period, or at least what I'm calling ancient, maybe not ancient for anybody who does hard rock science out there, but what I'm calling this ancient time period when we know that the Mississippi was flowing on bedrock. So we know that the Mississippi River was once deeply incised. This is related to the integration of the Mississippi River prior to the last glacial maximum. So when the Mississippi River, as we know and love it, was initially formed. And we actually have this amazing data set from the Minnesota Geological Survey where they were able to create an interpolated depth to bedrock map. So this is just showing that with our valley center line on here. And what we're able to do is something similar to what I did with the terraces, where I connected these interpolated bedrock depths with this modern valley center line, and I was able to create an approximate buried ancient bedrock profile. And this is what I came up with. And so we again have this modern valley centerline. And then we have this green here showing those interpolated bedrock depths. And we're able to sort of trace over that what we think the ancient bedrock profile may have looked like. There's also additional work that I'm doing with several folks in our group, working with seismic refraction and other passive seismic techniques to actually get more direct constraints on this profile because this data set is interpolated. But it's really interesting to see what we sort of hope and expect to see underneath the modern valley centerline. So what we can say about this time period is that there's a deeply buried bedrock valley that shows this deepest extent of glacially driven incision and base level fall on the Whitewater River. So just summing it all together and telling our story as I've sort of been able to parse it out so far, we have this ancient buried bedrock valley that records a period of deep incision from this time period when the Mississippi was very deeply incised. Then we have a period of aggradation and occupation of two terrace levels that are preserved in the modern Whitewater River Valley. And then moving into today, the modern river still preserves a nick point and has a channel lung profile that still shows that the river is working through the impacts of this glacial base level change today. And then finally, just a little teaser since I only had 10 minutes. As Andy mentioned, I'm working on some other cool projects. So I'm also doing some work with optically stimulated luminescence and cosmogenic temporalium dating to try and understand changes in erosion rate in this watershed during this time period and linking that to changes in climate and vegetation. And finally, I'm also interested in some work on the impacts of agriculture on erosion in the Whitewater, which has been pretty dramatic. And Jimmy and our group is mostly focusing on this, but I'm also interested and excited to use some of my geochronology work to understand the impacts of agriculture on erosion. But yeah, that's my little research overview. So thank you.
We have time for a couple questions, and I'll walk around with the mic so our guests on Zoom can join us.
Thank you for the fascinating talk. I thoroughly enjoyed it. Can you go back 3 slides where you reconstructed the these profiles? So just from the left diagram that you explained earlier, were you able to more or less predict what you will be recovering on the right? And if so, by having this more detailed profile, what additional can you learn, and can you give us more context about knowing this? Is it more about understanding exact profile and what contributed to it, and then trying to predict to the future? I just want to have more context about, motivation.
Yeah, well, I'm happy to talk more about that. So basically, yeah, we did have some expectation of what we would see based off of what we know is happening in the Mississippi. But some of the interesting things that are coming out of this work, like I mentioned with the OSL dates, is we're able to actually get a sense of how the nick point propagated upstream and get a better understanding not only like for how river systems in the upper Mississippi River Valley responded to that upstream nick point propagation, but also because we have such good constraints on this base level change, I'm hoping to be able to say more general things about how river systems respond to base level change and have this sort of serve as a controlled experiment for how we can understand, this sort of complex response. Not only do we have it moving upstream, but there's lithologic impacts. There's also impacts, the Whitewater has its own tributaries. How does that complicate the story? So we had some expectations, but we're hoping to learn a little bit more as well.
Thank you.
Any other questions? Well, thank you, Peter, for your question. Thank you, Shanti, for this excellent presentation. And let's thank Shanti one more time.
Well, with Shanti's nice presentation, I'm convinced that she has earned this award. So let's give her the certificate. So I would like to invite Professor Wickert to come together with me to present the award to you. Yeah, why don't you stand in the middle? Yeah. Congratulations again. Yeah. Now let's move on to the next part of the program. And as a SAFL tradition for student award, we always invite a distinguished researcher from outside to give a lecture on their research. Okay, so today, okay, we will have the same honor, and I'm going to invite Professor Peter Kang. Professor Kang is also serving as the chair of the SAFL seminar committee currently, and so Professor Kang will do the introduction.
Thank you, Lian. Hello, everyone. My name is Peter Kang from Earth and Environmental Sciences, and it's my great honor to introduce Dr. Ken Belitz. This is sponsored by actually GSA, Geological Society of America, and it's Marshall Dre's Distinguished Lectureship. And Dr. Belitz is 2023 winner of this lectureship, and we are fortunate to host him for this special day. Just few comments about Dr. Belitz. I think there are many things Dr. Belitz contributed to the field of hydrogeology, but it's very notable that Dr. Belitz led several mega projects in hydrogeology, and especially it led to the significant improvement in hydrogeologic framework, as you will see some of the examples here. And numerical models has been always a key tool that Dr. Belitz used, and recently machine learning. And today's talk will show you how machine learning has been combined into the hydrogeology field to address old problem with new approach. So yes, now the floor is yours.
No green. Oh, no, it's okay, great. The work I'm presenting today was done by a large number of people associated with the National Water Quality Assessment Program. And one of them is here, Mindy Erickson, and I'll show you some of the work that she's done as part of this presentation. Of particular note, Tom Nolan was a scientist who retired from the survey, and he's the person who brought machine learning into our groundwater quality modeling approach. And I'd also like to thank Paul Stackelberg, who provided leadership to a team of people that collectively leveraged each other's efforts to produce the kind of work that I can share with you today. My presentation will have 5 parts. Normally I like to have 3, but I have 5. Introduction and conclusions are really quite brief. The meat of the talk, the heart of the talk, will be overview of Ensemble-Tree Machine Learning. Then I'll introduce a feature that we developed, multi-order hydrologic position, and then I'll show you some applications to groundwater quality mapping. By way of background, this work was done as part of the NAQUA program. Back in the late 1980s, the chief hydrologist was appearing before Congress, and he was asked the reasonable question, what is the quality of the nation's water? And the answer is he didn't know. And fortunately, the survey wasn't punished for that response, but instead, Congress provided funding to answer that question. So the motivation was, what is the quality of the nation's water? Is it getting better or worse? And what are the factors affecting water quality? And before I continue, I am from New York, and I may start to speak really fast. And so please stop me. It won't be interrupting. It'll be doing us all a favor. The NAQUA program has been implemented in surface water, ecosystem, health, and groundwater. The NAQUA program was implemented in decadal cycles. There were 3 cycles from 1991 to 2021. The funding has been in place for this project on a continued basis, but it's no longer centralized. The funding has been distributed to a number of projects supportive of this goal. We're going to focus on groundwater quality. It's one of those 3 components. There were 3 monitoring networks in place for cycle 3, designed to address the question, what is the quality of groundwater in 3 dimensions? And the thickness of those maps are relative. We have a set of land use studies, typically observation wells, 20 to 50 feet deep. We have a set of major aquifer studies. Major aquifer studies were generally distributed within a small to medium-sized watershed in areas where a large number of people depend on domestic wells. In the 3rd cycle, we had a new component, principal aquifer studies. These were studies of public supply wells. They're typically 150 to 750 feet deep. In cycle 3, we sampled about 4,000 wells, and that's about 13,300 person days of work. And our field crews typically put in a 10-hour day, and that's roughly 130,000 hours just to acquire the samples, to give you some sense of the scope of work that I'm reporting here. One of the graduate students today asked me, how do I get my data? It's like, well, you supervise people who supervise people who get the data. It's a true team effort. That's the monitoring side of how do we assess groundwater quality in 3 dimensions. Today, I'm going to speak to you about the modeling side of that. At the outset, we decided we would focus primarily on groundwater use for drinking supply. The reason is obvious. Taxpayers pay our bills. They're the ones that we're going to try to provide information for. We focused on constituents prevalent at concentrations above a health-based threshold. This wasn't about our favorite constituent. I like selenium, so I'm going to study selenium. We collect the data. We measure those samples for more than 500 constituents. About 300 of those constituents have a health-based threshold. Those that are high across a large landscape are those constituents that we chose for modeling. We initially identified 4 principal aquifer systems for evaluation. A principal aquifer is a large, extensive aquifer system providing substantial amounts of water for human use. The glacial system in which the state of Minnesota sits, the Central Valley in California, the most productive agricultural system the world has ever seen. North Atlantic coastal plain, home to tens of millions of people. The Mississippi embayment, home to a large number of people and also a very productive agricultural industry. As we progressed, we sampled, or rather we modeled more than just those 4 areas. So I'm showing you a map, the upper right, which is alluvial deposits in the Western United States. And we've also modeled nitrate across the entire continental US. In order to do this modeling work, we relied on data that we collected as part of the NAQUA program. We relied upon the entire USGS data set, and we relied on other sources, including data collected under the Safe Drinking Water Information System Act. That's the introduction. This work is done by NAQUA. A large number of people are involved. I ran that groundwater component, and I will represent the work of a large number of people. The next part of this is an overview of Ensemble-Tree Machine Learning. Many of the things you see in this section will be repeated, but I want to just introduce it in the context of like a little bit of a tutorial, so we have a vocabulary. Let's start with decision trees. The purpose of a decision tree is to estimate the value of an unknown response variable given known values of a predictive variable. In the machine learning community, they call these features. A variable can be categorical or quantitative. A well can be located in the glacial system or not. A well can be 300 feet deep or greater, or it can be shallower, right? So it can be continuous or categorical. Then for a set of known data, we're going to build a tree. So the top box has all the data. I'm going to ask a question of that data. Which feature and what value of that feature best separates all those data into 2 groups such that the variance of those 2 boxes is minimized? So the box has a mean and a variance. You split it into 2 boxes. We want to reduce that variance most effectively. So every one of those boxes is a node or a split. And at every box, we're simply splitting the data into groups, minimizing variance. And then we'll stop when we reach those ovals, which are terminal nodes or terminal leaves. We will specify a priori the minimum number of data remaining. That's a variable that you can tune to. For regression problems, you typically stop at about 5. For categorical problems, similarly. After the tree is built, it can be used for new cases. A simple single complex tree, I should say a single complex decision tree can be well trained. So you take your data, you split it out, and then when you pass the data back through, it does a great job of prediction, but it doesn't generalize to new data very well. And so decision trees have been around for a long time, and it's been known for a long time that they fail to generalize. The brilliance of a number of workers at Berkeley and Stanford was that they recognized that if you introduce randomization into the construction of trees, you can overcome this problem. So there are several ways in which randomization is introduced. The first is that each tree is built with a subset of all the data, and the number is 2/3. And then at each, so we have a large number of trees shown by those little symbols. And then at each split, we're not going to look at all the predictive variables. We're only going to look at a subset. So we have 2/3 the data, and then we have a split. The algorithm will select roughly 2/3 or so, and I'll explain more about that later, of the data. And then for each one of those predictive variables, for each one of those features, it will find the feature and the value of that feature that most effectively splits this box of data into two. It gets to the next split, and this is sampling, with repeating. So at the next node, you again select a set of parameters. In the vocabulary of the R package, it's called mtry. And we can repeat this 100, 200, 1,000, 2,000 times. In the jargon of random forest, these hyperparameters, the parameters that make the model work, are mtry, the number of explanatory factors used at any split, entries, the number of trees, and node size, which is how many data you choose to stop doing splits at. If we have a categorical response variable, it's random forest classification. We have hundreds or thousands of trees. It's by majority votes, where you pass your data through each tree. The tree makes a prediction, yes or no, black or white, 0 or 1. Majority vote, each tree gets 1 vote. With continuous response variables, that's random forest regression, and it's the average of the predictions made by each tree. Again, in the jargon of random forest, each tree is a weak learner, but the ensemble can be a robust estimator. So that's random forest. That's one version of ensemble trees. It's an ensemble because there's many, many trees. Boosted regression trees is another version, and it's based on residuals. So I'll walk you through a set of slides, a set of images that Paul Stackelberg prepared. What we're going to do is, first of all, select the parameters. Those parameters include things like tree depth, number of trees. There are many others. The boosted regression tree algorithm has more tuning parameters, more hyperparameters than the random forest. The initial prediction is simply the average of all the data. We can compare that average to all of the observations and obtain a residual. We then are going to build a decision tree on those residuals. Having built a decision tree on those residuals, we can run each of the samples through the tree, and we're going to get a new residual because it won't be perfect. So we have a new set of residuals. And rather than add those residuals to the previous answer, we're going to downscale it by a learning rate. If we multiply it by 1, you'll overtrain it. For those of you old enough having models, say, in finite differences, this is under relaxation, right? That when you do numerical approximation towards a solution, you don't want to overshoot. So the learning rate is comparable to under relaxation, that you're just taking a fraction of the prediction and adding it to the previous result. We update that current prediction, and then we repeat this n times, and we have some closure criteria to determine when to stop. And then finally, we get a final prediction. So boosted regression trees, excuse me, is an alternative. It was designed for really hard problems because these models run more quickly. But my experience, random forest runs really quickly on these earth science data sets that we've been using. But as is the case in much of research, people feel compelled to use the latest version of something, and boosted regression is simply more recent than random forest. With that said, I'd like to share with you some thoughts on model development based upon our having built tens of these at this point. This is well known. Ensemble tree models are prone to overtraining. What we do is we train the model on 80% of the data, and we withhold 20% of the data for testing later. Then there's this issue about model tuning and the selection of optimal parameters. It's currently de rigueur to optimize the selection of hyperparameters by tenfold cross-validation. You take 90% of your data, you fit a model, you run all the parameters on it, you put those data back in, you sample again, and you repeat. Or you could do it by trial and error. For random forest, there are only 3 hyperparameters. It's easily doable. In boosted regression, there's many more, and so it tends to be automated. However, default parameters often work just as well. But if you're writing a paper, submitting it to a journal, they're going to insist that you go through this procedure, even though default parameters work about as well. The next issue I want to address is one of model complexity. It's a term that's used a lot in this setting, and it's typically used for describing the structure of the ensemble of trees. Well, random forest is not particularly complex. There are only 3 hyperparameters. The boosted regression, also called gradient boosting, is much more complex, and there are automated procedures for doing it. So again, there are folks who develop these routines. They package them for Python or R. People use the latest one to automate this procedure. It's repeatable and therefore has appeal. There's another type of complexity, which in my judgment, now that we've done a lot of this work, is equally, if not more important, and it's a number of predictive variables. When we began this work, Tom Nolan was trained as a statistician. He has a degree in agricultural engineering, and he had a very strong statistical view that just throw all the parameters in there and let the model choose. As an expert, you might decide, there's really only a few important variables, and that's a reasonable approach. But from some perspectives, that could be called bias, right? So there's this one view, it's expertise, and someone else's view, it's bias. So you can use recursive elimination to remove predictive variables. So I'll show you a plot in a moment where the variable judged to be the least influential is removed, and then you systematically remove variables till you reach some point. Alternatively, you can use expert knowledge. Expert knowledge, can be used ahead of time, looking for variables that correlate and just removing those that correlate with others. One can look at a bunch of diagnostic plots and use one's judgment. So let's move from model development to model assessment and interpretation. And please don't read the words that you see on these plots. They're just for illustration. This is a variable importance plot. Each one of those rows is simply the name of the variable. Doesn't matter what it is. The length of the bar is its relative importance. That is automatically calculated in the random forest algorithm. It's calculated with a post-processor in boosted regression. And right away, you can order it and determine which variables are most influential. The variable importance plot is used routinely in recursive elimination of features. So the ones in the bottom are the first to go, rebuild the model, etc. However, and this is really important, a variable can be important locally, but not globally. So what do I mean by that? Imagine you have 1,000 outcomes, and 100 of them are just different than the others. And 900 of them are all kind of comparable to each other. The most important feature for those 100 doesn't stand a chance at being one of the most important variables because it's only important for 100 cases. So this plot's important. It tells you a lot, but being at the bottom of this list is insufficient for rejecting it because there could be other reasons why it's important other than its global importance. Whoops. And also show you another example of a variable that has very low importance. It appears really low in this chart, but it's systematic. So why would you ignore something that systematically affects the outcome in a very predictable way? Even if it's only a small amount, it's still systematic. Another diagnostic plot that's really useful is the partial dependence plot. Again, you don't need to worry about what those axis labels are. The x-axis is our feature. The y-axis is our outcome. And if you look at the shape of that curve, you can see that as our feature increases, our outcome increases. It's systematic behavior. With expert knowledge, you can ask, is that systematic? Is it real? Here's a version of non-systematic behavior. And non-systematic behavior can be caused by a number of things. And here's two that I can mention. One is variable interaction. So I'll use the word soil bulk density. Ignore that dip. What you see is that it starts at 1 and it gets about 1.1. Ignore what it does until 1.4 and it goes down again. One possibility, we didn't explore it, whenever soil bulk density is between 1.2 and 1.4, there could be some other variable that's important to this outcome. And while that variable is important, this variable is not. When that variable goes away, bulk density is there again. So it doesn't mean there's anything wrong. It just tells you there may be something more going on. And a plot of your outcome against a single variable may be insufficient. Another feature, and you may see this, let's see if this will work. No. On the bottom of that graph of soil bulk density are a bunch of blue tick marks. They're called rug marks in the algorithm. Those are the deciles of the distribution. So oftentimes one will see some kind of unusual behavior but its behavior just on the outliers of the data set. So that's a very useful, those rug marks are really useful for getting interpretations out of these models. Non-systematic behavior, however, can also be an indicator of location. So for example, there is a portion of the landscape where something has happened that's the outcome you're interested in. And it turns out it just happens to be at a certain elevation. Elevation didn't cause it. It's not correlated with it. But the model is going to see that elevation is in fact associated with that outcome. So the non-systematic behavior can also simply be a pointer that you're dealing with a variable that in and of itself is not the process, but it's telling you where spatially something is happening. Most recently, a way of looking at these data, the SHAP plot has been developed, the Shapley additive explanations. So I'll explain this one a little bit more. Again, the actual labels don't matter. The outcome variable, the predicted variable, is increasing from left to right. And what we're going to do is calculate the influence of each feature on each data point. So the top feature is the one that through this algorithm is judged to be most influential. These are the top 10 features out of more than 100 that were evaluated. Then you see colors. A yellow color is a low value of the feature. A purple color is a high value of the feature. So let's start with something that goes from yellow to purple. The number 2, which is, I can't even read it. The second row, you'll see it goes from yellow to purple. So we're going from a small value of that feature to a large value of that feature. And you can see that the predicted outcome is increasing as you go from low to high. That's a positive correlation. So the direction of the relationship can be identified. And I've already mentioned the most influential features can also be identified. So the SHAP analysis is a bit of a combination of the variable importance plot and of the partial dependence plot. This is useful because it can be done on a post hoc basis. So for those of you who've already built machine learning models and you have not withheld data in the testing, you can still go back and build a SHAP plot on it. What's also particularly helpful about the SHAP analysis is that it can be computed for all of the data points or a subset. So we have this suspicion that there are these 100 outlying values, the outcomes. We can just do a SHAP analysis on those 100 and then find what features are important for those 100, even if they're different than the other 900. And by systematically, what I'm trying to do is all these plots are coming from various publications put together by members of the Nautical Groundwater Group. The last piece of general talk I want to provide here before diving into the next phase is really important. Ensemble tree regression is prone to second order bias. Second order bias means that large values are underestimated and small values are overestimated. So the left-hand plot is observed pH in the glacial system, the machine learning plot on the left, on the y-axis. So you see, for example, where the observed pH is around 10, the predicted value is between 8 and 9, underestimating. If you look where the observed pH is 4 to 5, it's predicting, around 5, overestimating. And this is absolutely a necessary part of ensemble tree learning because it's a binning and it's an averaging. Right? So you just can't get those tails. An alternative way to look at this problem of second order bias is to plot the cumulative distribution function. The blue is the observed, the orange is the machine learning. So if you look at the larger values of pH around 8 or so, you'll see the orange value plotting to the left. In contrast, for the smaller values, 5 to 6, the orange is plotting to the right. Without going into the details, we've identified a way to fix this problem, and it's empirical distribution matching. I have met some of the graduate students. There are people here working on satellite data. In the satellite community, they call it data assimilation, where you've got a CDF for your satellite data, cumulative distribution function. You have a cumulative distribution function for your observations. And from that rank order relationship, you can rescale your data. And it works beautifully. So that's an overview. So if you're now feeling like you've already heard too much, you could probably just allow yourself to kind of step back, not worry too much about multi-order hydrologic position, and just enjoy the colors. I developed multi-order hydrologic position because if we're going to map groundwater quality on a wall-to-wall basis for the entire United States, we want variables that are relevant across that full landscape, with edge to edge. So we're going to define a concept of hydrologic position. So here's just a cartoon. The line is a stream. The blue area around it, shaded in gray, is its watershed. There's a point in that watershed. There's a distance to the stream, and there's a distance to the divide. And we're going to define a term called lateral position. In the numerator, we have the distance to the stream. In the denominator, we have the distance to the stream plus the distance to the divide. That's dimensional, 0 to 1. And here's just kind of a cartoon of what that looks like. It doesn't matter how big your watershed is. It could be tiny. It could be huge. There's a relative position. The other term we're going to develop for hydrologic position is the distance from the stream to the divide. The distance from the stream to divide will have units of length. It will not be dimensionless. It will tend to be small where two streams come together, and it will tend to be large in the upper watersheds. So let's take a look at what this looks like first for LP and then DSD. This is a tiny little watershed in Wisconsin. The dark blue lines that you see are the streams, and then the black lines you see in the field of yellow are Tyson watershed divides. These are not topographic divides. A Tyson watershed divide separates all points closer to a given stream than to any other stream. So it's just like Tyson polygons around a rain gauge, but this time it's a Tyson polygon around a stream network. So the lateral position has values of 0 at the stream, and it has values of 1 at the divides. So you can see that on the left. Now what we're going to do is take our pencil eraser and remove all first order streams. In the world of Tyson, a second order stream becomes into existence when 2 first order streams join. A third order stream comes into existence when 2 second order streams join. If a first order stream joins a second order stream, it remains second order. So for this watershed, we've now drawn the order 2 streams. So you can see there aren't very many of those. We've redrawn the Tyson divides around each of those streams, and we've recolorized 0 to 1. Then there's only 1 stub of a third order stream in this tiny little watershed. And so you can see the pattern. So you see the black lines. We don't see any other third order streams. So everything goes from 0 to 1. So imagine any point on that landscape. It could be in a first order stream and have a value of 0. It could be in the second order stream and have that value of 1. And it can be in the third order stream and have an order of 5, right? So you just think of it as its position in each of these stream networks. Now let's look at the distance from stream to divide. When 2 streams come together, the distance from stream to divide becomes 0, right at that intersection. So the distance from stream to divide is going to be small at a confluence. So those bright spots of orange color are at the confluences. And I include the streams here purely for illustration because this is a pixelated map and those streams no longer really exist. All that exists in every pixel is the distance from stream to divide. And so look at those distances on the first order network. Those oranges are 0 to 400 meters. And then you see the largest value of distance from stream to divide occurs when you're far away from a stream, and it's on the order of less than a kilometer. Then we go to the second order stream network and we see some oranges, and then you go to the third and it's all that mustard color. And that mustard color, is on the order of a kilometer or 2. So distance from stream to divide is the second address, in a sense, that can be had. The last thing I'll say before going to maps United States, so lateral position is in essence a function of how far are we from the stream in a lateral position. Distance from stream to divide is analogous to distance from the confluence. It tends to be small at the confluence. It tends to be big in the upper watershed. Let's think of LP, lateral position, and DSD as latitude and longitude, but it conforms to the hydrography. So I'll show you some images. One of the fellows working with me, his parents are about 10 years older than me, and he sees these images and says, Ken, that's really groovy. So order 9, the Mississippi River is more than order 9, but we stopped at order 9. The oceans, the Great Lakes, the Gulf of Mexico were taken as order 9. So you can see that top left is lateral position for order 9, and you can see really big pieces of landscape. You go to order 8, order 7, order 6, suddenly you start to see a lot of streams. Look at order 4, you can't even see anymore, what's really going on. So we're going to take just that small piece of Wisconsin, or a small piece of Wisconsin. Order 4 is now blown up, and order 4 at that scale looks a lot like order 8. Take it down to order 2, order 1, again, you won't see it. So we have here then is 9 hydrologic orders, and we have, in essence, let's call it a longitude, right, with respect to every one of those stream orders. Let's switch to DSD. Just look at the colors. Order 9, look at those greens. Those greens are on the order of hundreds of kilometers. The distance from stream to divide for the 9th order stream network over most of the nation is hundreds of kilometers. There's a pixel in there where they come together. It still has to be on the order of, just a couple hundred meters, right? Or even 30 meters. But there's so few of those that you can't see it. Look at order 2. And again, I've laid over the blue streams just to help organize it. But those blue lines are not really there. So look at all the orange that begins to show up because it's really small. So you can be at a divide. In fact, that's why I'll show it. Look at the order 2. You see the spine of yellow in there? So if you go back to the previous map, you can see that same spine of yellow, right? But you'll see yellow everywhere on that map. So how can you distinguish LP equals 1 in one area from LP1 in a different area? Oops. Well, that's because you can have LP1 and a large DSD in one place, and LP equals 1 and have a really small DSD in another place. So every point in this landscape, in essence, has a unique address. So to summarize, multi-order hydrologic position can be used to characterize hydrologic systems. There are 9 hydrologic orders and 2 metrics per order. We have wall-to-wall coverage for the conterminous United States. That's 9 billion 30-meter pixels. This provides a basis for machine learning over a range of scales. When we built our machine learning models, invariably 2 or 3 of these MOHP variables shows up, but the order that is important differs. Lateral position is independent of basin size or order. It's a measure of distance from stream. It's dimensionless. The distance from stream to divide is dependent on basin size and order. It's an indirect measure of distance from confluence and drainage density. LP and DSD are analogous to latitude and longitude, but conformable to the hydrography. So that's the first part. Hopefully I haven't lost you. There will be 3 case studies. The first and the third are relatively simple. The second one is really quite complex. And I'll try to walk you through it if I can. Let's start with nitrate and groundwater used for drinking supply in the continental United States. This was the boosted regression tree model, 12,000 measurements, 80% were used for training, 20% for holdout. Katie Ransom initially considered 187 features. She retained 76. Well depth was the most influential feature. I didn't really know it at the time, but I can say it now. When you have a model with 76 features, it's about as complicated as the world itself. And one of the reasons we model is to simplify and understand the world. It makes a great model. If our goal is prediction, we did great. If our goal is understanding, we still have a job. Well, we then used this boosted regression tree model to map nitrate concentrations at a 1 kilometer spatial resolution. That's 8 million pixels or voxels in the United States for 2 depth zones, the depth zones used for domestic wells and the depth zones used for public supply wells. Well, we also mapped that. I won't get into how we mapped it. So in order to make something like this work, we're not just working on the outcome variable, but we're also developing these features. This is a map of groundwater quality at the depth zone used for domestic supply. The drinking water standard is 10 milligrams per liter. The pixels that you see in yellow are above the drinking water standard. The pixels you see in blue are less than 1. So that was the outcome. Now, the R squared on this, and I was talking to one of the postdocs earlier today, was terrible. It's like 0.4 or something under testing. It's just awful. So what we're going to do is ask the question, with an R squared that low, what does the model tell us? And so an alternative to evaluating a model at every single point is to evaluate the model's performance at a larger spatial scale. And so what we're going to do is evaluate nitrate at the scale of what we'll call hydrologic regions. The US Geological Survey in 2003 provided a map of what are called principal aquifers. There are 58 principal aquifers in the continental US. And then in 2018, I mapped secondary hydrologic regions. Why? So we can fill out this map wall to wall. There are 56 hydrologic regions with more than or equal to 25 data points. Why 25? Because the percentage of high values is 4%. If you want to see a single value in a data set at 4%, 25 is the number you get. So any HR with fewer than 25 data points, we're just going to set aside because we don't have the opportunity to really test it. That's the training side. For testing, it was 20% of the data. There are 25 HRs with more than 25 or equal to 25 data. This is a complicated plot. Please allow me to explain it to you so you don't try to read ahead of me. And if you read ahead of me, I'll just talk faster than you can read. The left-hand side is bias-corrected estimates. The right-hand side are the initial estimates before we used our bias correction. Don't look at the colors. Don't look at the symbol shadings for now. Look at just the spread of symbols on the bias correction or all about on either side of the line. Look at the ones on the right-hand side. You can see they're lifted. The blue ones are lifted. The orange ones are plotting almost entirely along the bottom axis. Now let's look at what those symbols mean. The orange colors are greater than 10. The blue colors are less than 1. The open symbols are training. The filled symbols are testing. I'm going to ask the following question. For a given hydrologic region, what proportion of all the wells in that region have a high value, greater than 10? Alternatively, what proportion of the values have a small value? For the same region, we can ask the question, what proportion of the predictions are high? What proportion of the predictions are low? So far, so good? Let's start with the left-hand plot. Let's start with the low values. The observed percent, let's look at 80%. So let me back up. Each one of those data pairs is a single HR. And so we can ask the question for that HR, what was the observed proportion and what was the predicted proportion for low values? And so, for example, here, the observed is 80% and all the predictions are here, right? So we over-predicted low values or proportions because we failed to see them. Then look at, whoops, I keep thinking it's a pointer. Look at all those orange values. We have a lot of observations of high values, and yet there are no predictions. The model failed to predict all those high values. So let's look over on the left-hand side. Look at those orange values. In observations, we have as much as 20% high values in our HRs. And then you can see how the orange values all lifted after bias prediction. Then the blue values all drop back towards the one-to-one line. Had we not done bias prediction, we would have failed to predict any high values. We did a very poor job at the point scale. We did a very good job at the regional scale. So there's a certain amount of humility one should bring to it, but it doesn't mean the model's bad when you have a low R squared. I would encourage you to look a little more closely, ask the question, where does the model fit and where does the model fail to fit? You know, what scale? So that was the relatively easy one. Yeah, sure. Well, this is groundwater. So there were over 100 when she started. So everything you can imagine is put in there. Recharge rates, 30 or 40 different soil conservation service variables, depth of wells, kinds of materials, all kinds of things. Yes. All of the features are available as maps. because if they're not available as maps, they can't be used in the prediction phase wall to wall. Because most of the United States doesn't have a measurement of nitrate. And therefore, if we want to make a prediction at that point, we need to have something already measured. So for example, one could build a model of nitrate concentrations using measured dissolved oxygen, but we don't have measurements of dissolved oxygen everywhere. So in order to make a prediction on a wall-to-wall, top-to-bottom basis, we need to have variables that are available wall-to-wall, top to bottom. The groundwater quality in the glacial aquifer system will give you an example of exactly that. Why study the groundwater quality in the glacial aquifer system? 98 million people reside within the footprint of the glacial aquifer system. 6.3 million people are served by domestic wells in quaternary deposits on that footprint. 23.4 million people are served by public supply wells on that footprint from quaternary deposits. Arsenic and manganese are prevalent at elevated concentrations. Aqueous concentrations are controlled in part by pH and redox. In geochemical circles, pH and redox are called master variables. We mapped pH and redox in 3 dimensions. We don't have measurements everywhere in 3 dimensions, but rather we mapped it. So let's start with these maps of pH and redox. Then I'll introduce another master variable, and then I'll show you the results for arsenic and manganese. For the redox models, the work was by Mindy Erickson, who's here with us now. She had 9,000 plus dissolved oxygen measurements, 17,000 plus iron measurements, using more than 50 features. And this is the resulting map. The areas you see in gray, there is no anoxia at depth. The areas you see in blue are a relatively shallow depth. The areas you see in those brighter colors start getting deeper. For the pH model, more than 18,000 pH measurements, 97 features. The reds are pH is less than 6.5, almost entirely in the northeast of the United States. The blues are greater than 7.75, mostly in the west. So just to show you what it can look like when you get there. So we had, 18,000 measurements is a large number. But this is 1 kilometer pixels. I'm going to guess that the glacial aquifer system must be on the order of 2 million square kilometers or so, maybe 1.5. That's 1.5 million voxels, because we're doing this also with depth. So 2 of our master variables were pH and dissolved oxygen or redox. Another master variable that's really important is groundwater age, groundwater flow path. The longer the groundwater flow path, the more interaction with rock, the more opportunity to pick up dissolved constituents. So flow path length and also just time, just with enough time, things can dissolve. So we developed what we can call a meta model. We developed 115 mod flow models for the glacial aquifer system. Collectively, that was 26% of the total area. Each one of those mod flow models had a 1,000-foot grid cell. The glacial aquifer system was divided up into 3 layers. There was 1 bedrock layer. The variables in this model was the hydraulic conductivity of coarse-grained glacial deposits, which we mapped, the hydraulic conductivity of fine-grained glacial material, and the hydraulic conductivity of bedrock. It's a very simple modeling concept that streams should flow and uplands should be dry. So there's 2 kinds of error that can happen in a model. If the permeability is really high, the water table just drops because it doesn't take much for the water to move towards a stream, but all the streams basically go dry except for a few spots. So if the hydraulic conductivity is too high, you wind up with a lot of dry streams in the model. If you make the hydraulic conductivity low, the water table rises. If you make it high enough, it floods everywhere. So there's 2 kinds of errors. It's just a balancing of those 2 errors to develop these models. So Jeff Starn is the first author on this work. And Jeff is a fine programmer. And we put this tool into the hands of a couple of people, and they developed these 115 models. Once these models were generated, we then use mod path. So first we use mod flow, then we use mod path. A swarm of particles is put on every single landscape piece, and we just track it through. And then in every voxel, we can calculate things like flow path length. We did that for 1% of all the model cells at 131,000 locations. Well, we have a complete age distribution for these 131,000 voxels. We have a complete distance traveled. We're going to simplify it because we don't want to be giving the machine learning model too much information. We computed at each one of these voxels the fraction of young groundwater. Why do we use 65 years? 1950 was the onset of atmospheric bomb testing, and that left a tritium signal that we can still detect. We calculated the mean age of that young fraction, and we calculated the median age of the old fraction. Why median? Because there are some really long tails, and we don't really want that to bias the mean too much. Oops. So we simplified our mod flow and mod path information, and we then treat that as data. We're going to build a machine learning model based on outcomes from a process model. That's a meta model. So let me pause here for a second. So back to your question about measurements. We don't have measurements of pH everywhere. We had measurements of pH at 18,000 locations. We leveraged those pH measurements so that we could then have wall-to-wall, top-to-bottom pH. So these age metrics and flow path length were then used as response variables or predictive variables or features for training a boosted regression model. The predictive variables included in this BRT model were all of the things used in the groundwater flow model. Like we knew what the recharge is, we have the thickness of the aquifer, we used MOHP, multi-order hydrologic position, and a few others. We also generated a BRT model for saturated thickness because the ratio of recharge to saturated thickness is known to have a strong control on groundwater age, right? If you have a really thin aquifer, the groundwater age is young. If you have a really low recharge rate, then it can be old. Again, a machine learning model trained on the results from a process model can be defined as a meta model. 4 meta models were developed. And then these models were used for estimating pH, redox, arsenic, and manganese. So now let's spend a little time on this SHAP plot. So now we can pay attention to these labels. Groundwater age increases from left to right. The most important variable, most important feature going through this algorithm is the relative depth of the well. Where in the column is it? The second most important is tau, sediment thickness divided by recharge rate. Let's look at LP1 for a moment. LP1 is lateral position. It takes on a value of 0 at a stream. It takes on a value of 1 at a divide. When you're at a divide, groundwater, this is, the groundwater is just entering the system, so it should be relatively young. And as that groundwater flows through the subsurface, it comes back up to the stream, it should be old. So a red value is large. That means LP1 at the divide. A blue value is small, LP0 at a stream. So we're seeing ages systematically increasing as we go from divide to stream. I highlighted those MOHP. The first and second order stream net is controlling groundwater age to a great extent, which we'd like to see. And then we see DSD9 and LP8. If you recall those maps, those were big features. This is sort of telling you, are you in the western part of the glacial area or are you in the eastern part of the glacial area? Are you closer to the Great Lakes or further from the Great Lakes? Okay. So this is an example of interpretable machine learning. We can actually make a relationship between these explanatory factors, and these explanatory factors are not random. And they're relatively easy to interpret. Now I want to show you some images, again, pointing out how these models can tell us something consistent with our expectation. This is the distance traveled from the point of recharge to a voxel. So layer 1 is the top of the system. Layer 9 is the interface with the bedrock. So you'll see a bunch of orange colors. That's on the order here of about 100 meters to a kilometer. The greens are on the order of 10 kilometers. So the deeper part of the system, it takes longer to flow to get to that depth, right? It's a longer distance traveled. This may be washed out because the next image is really kind of cool. It still shows up. So this is a blow up around Wisconsin and then towards Minnesota. I want to call your attention to the area, west of Green Bay, where you see that river. I think that might be the Missouri, right? Going up there, that nice yellow line. For those on Zoom, I apologize. I don't have a pointer. So this line here, Mississippi. So you see all of those headlands, relatively small distance of travel. You get to the Mississippi, large distance traveled, right? And if you start to stare at this image, you just see incredible detail. We're painting a really broad landscape with a really fine brush. This may not be real, right? Because what this is really reflecting is that we have fed the machine learning model things like LP, a lateral position. We fed it things like multi-order hydrologic position. We've given the machine learning model the paintbrush, and it's painting by colors, in essence, right? Where is LP1 equal to various values? My guess, without knowing, I'd have to now do a shaft analysis. You see all those green areas? That's probably where DSD 8 and 9 started showing up, because it's just separating one area from the other. Finally, let's get back to arsenic and manganese. I'm not going to show you the maps. That's the little thumbnail sketch that was in the ES&T article. Just look at the colors. Don't worry about anything else. In red are the redox variables. Redox is really important for arsenic in the glacial deposits. Not as important for the manganese, but it's still pretty high. So you see the red are the redox, the yellow is pH, the green are those meta-modeling parameters. MOHP was used in the groundwater age model. MOHP was used in the pH model. It was used in the redox model, but it's being used again. Machine learning has the benefit that one does not need to have independence of the features, independence of the predictive variables. So you can see that most of the things that are process-based are among the top. This is the top 20 features out of 79 for arsenic, out of 55 for manganese. So you can include process into these machine learning models in an a priori way. You can use expert knowledge. Our last case study is a little bit easier. It's the depth to the water table in Wisconsin. And the point of this one is to show you that a feature can be of low importance on a global scale, but still has systematic value. I built two models, one using observed depth to the water table for the entire state of Wisconsin, another using results from a simulation model for the Fox-Wolf-Peshtigo watershed, which is just a portion of the state of Wisconsin. We have 15,000 plus observations. We have 11,000 plus head values. I could have had more, but we didn't sample every grid cell. The depth to the water table in blue is 0 to 2 meters, in red 17 to 32 meters. So you can kind of see those various features. So we developed two different machine learning models. The features were land surface elevation and those 18 MOHP matrix, nothing else. This is a variable importance plot, and it is not in the order of the most important variable to the least important variable, but rather ordered in a way I can understand it. Order 1 to the left, then order 2, order 3, all the way through order 9. LP, DSD comes first, LP comes second. The most important variable on a global basis is land surface elevation. Let's look at a partial dependence plot for land surface elevation. The x-axis is land surface elevation. The y-axis to the left is for Fox-Wolf-Peshtigo. That's a simulation. The right-hand y-axis is the partial dependence for the observed depth of the water table for the state of Wisconsin. And I've offset those axes by 3 meters. Now that I've offset those axes, look at how similar those two curves are. I want to pause. One model is based upon noisy observations. The other model is based upon a really smooth data set. The observations not only are noisy because they're observations, they're also highly clustered. The model is perfectly distributed. And the machine learning model shows the same relationship between depth to the water table and land surface elevation. Then those dashed lines are that portion of the data that the land surface elevation is in the 98th or higher percentile. So we kind of just, put that on hold. So that's the most important variable. Now we're going to look at LP1. LP1 Look at the orange curve. It's about the least important variable there. In fact, let's pause for a moment. Now that I showed you the similarity for the partial dependence plot, look at the blue, look at the orange. To me, those two look quite comparable to each other. So again, machine learning model is discovering, within the vocabulary of this, the same information in a simulation model as it's discovering in observations. Let's focus on LP1 for a moment. Can we all agree it's about the least important variable? Well, let's look at that orange curve. It goes from about 10.5 meters to about 12.5 meters. Well, 2 meters change out of 20 or 30 is not a whole lot. That's why it's not so important. It's only explaining 2 meters. But I don't know about you, I want a model that tells me that as I get further away from the stream and I head towards the highlands, the depth of the water table gets greater. I don't want a model that doesn't tell me that. Had I rejected that variable based upon variable importance, I would have missed something. Useful tool, but in my judgment, not to be used by itself. In the so then, LP2 shows behavior quite comparable to LP1. Then you can see DSD, distance from stream to divide, is in fact more important than LP. It covers more range. For some people, this is intuitively obvious. For others, not so obvious. We often see streams in cross-section. We often see flow paths in cross-section. We often see a hillside flowing to a stream in cross-section, so it looks like groundwater is always flowing perpendicular to streams. Groundwater flows in the same direction as the stream, and that is downhill. So when you look at water levels on a map, those water level contours are pointing in the same direction as the streams. The groundwater flow paths are intersecting streams at an oblique angle, at a highly acute angle, not perpendicular. So it's more important to predict depth of the water table, whether you're near the confluence of two streams or you're up in the headwaters distal from that confluence. That's more important than walking away from the stream with your back turned towards the stream, simply, kind of in that perpendicular direction. So I showed this again to show that a variable of low variable importance can in fact have a systematic effect. And why would you exclude that from a model? So conclusions. I show this slide because of its simplicity. This comes from a model that Rosecrans developed for fluoride in the Basin and Range in Central Valley. We have measured values of an outcome variable like fluoride in wells. We have a whole set of predictive variables, and together that makes a prediction map. So if you remember nothing else, this is in essence how we've used machine learning. It's a way to leverage measured values, measured predictors to get a map. Now the word version. Ensemble-Tree Machine Learning need not be a black box. So often hear people complain about machine learning, it's a black box. It need not be. We have diagnostic tools, feature importance, partial dependence, SHAP, they're available. Process models and process features can be incorporated. There's no reason not to use, as this community of machine learners call subject matter experts domain experts. And by the way, the MOHP was reviewed by a colleague at the survey, and she pointed out that it was a really nice example of feature engineering. And I thought you needed to work at Disneyland to be a feature engineer, but apparently a geologist can as well. Multi-order hydrologic position provides a set of metrics to support machine learning over a wide range of scales. The lower order MOHP metrics, first and second order, are typically indicators of process. The higher order MOHP are typically indicative of location. Third order streams can kind of fit into either. Ensemble tree regression is prone to second order bias. Empirical distribution matching can be used to correct it. And with that, I've used up my hour, but I'd be happy to take questions.
Hello. In your introduction, you said kind of the guiding questions were about what's the water quality and is it getting better or getting worse? So how are you going to use machine learning to predict whether water quality will get better or worse? Maybe like for the arsenic example.
Well, arsenic is unlikely to change. Let's switch to one that would nitrate. And we are exploring nitrate changes in time on Long Island, New York. And machine learning is really great at interpolation, like most statistical methods, and relatively poor at extrapolation. So I anticipate that we will be using machine learning to infill the time series data so that we have a strong signal at a large number of places. And then we'll use process models and simplified process models to match that. And then we can use that in predictive capacity. But I don't think machine learning alone, this kind of machine learning will do it. Now, with that said, you will see people using machine learning for prediction, but it's typically at time scales relevant to Wall Street, like kind of days, because what you're really doing is feeding it information from the previous, 300 days, even 1,000 days. So you have sufficient information there to predict. But for something like nitrate, where it takes decades for things to move, and we only have a couple of decades of data. So there are methods that leverage a previous sequence in time, but those methods are not that great for groundwater data sets.
Use like a process model to feed your machine learning and then use the machine learning to.
Well, so there is something called deep learning, and I don't do neural networks. There's a penalty function in artificial neural networks, and people are building in process knowledge into those penalty functions.
Hi, thanks for your talk. It was really interesting. I have a question about model validation, because you alluded to it a little bit when you were talking about, one of those maps looking at, and you said, well, this may not be real. And so I will pose the question, how do you figure out if it's real or not, or how close it is to real? I think you're delineating like the river. Yeah.
So this is a great example of points versus ensembles. We have 582 tritium measurements in 431 wells in those 116 areas. 82 of the model areas have at least one of these. So here's the measured tritium on the x-axis, the calculated tritium on the y, and you can see that scatter. And then those triangles, what we're going to do is divide all of the measured tritium concentrations into deciles. Just rank order your data from largest to smallest, divide it up into bins of 10. And then for each of those bins, compute the average tritium concentration that was predicted. That's the triangles. So at that scale, I think it's a pretty great prediction. So the answer is you can. So in this case, we actually have observations, whereas, but one step before this is you can still compare the machine learning model to the ModFlow model. And that's why we always hold the 20% back. And for those of you who haven't been holding it back because you do tenfold cross-validation, prior to the SHAP analysis, it's very difficult to query the model again after it's built. And so by holding 20% out for testing, and by the way, on the subject of validation verification, is a paper by Oreskes and others. I'm an author on that paper. We choose not to use verification because it implies that this is somehow true, and we don't have access to the subsurface. So I prefer model testing or model performance as just a more neutral term. So in this case, we do have a kind of a confirmation that the performance is really pretty good. But we have data. There's no question that we're sort of lucky that way.
Thank you.
Yeah, great talk, Ken. And I had a question about the bias correction. And I think the best example of this was it nitrates, where you had done this second order bias correction, and particularly for the high values, you had not predicted any high values.
Yep.
Yes, that plot.
Well, actually, take it back. We did. So this is the training. So I take it back. We predicted these three.
Okay, right.
So this one's not too bad. The observed was like 35 and we're predicting 22. And that's percentage of all the samples, right? Okay.
And so after the bias correction, you get some distribution. And my understanding is you're doing some sort of a distribution matching. Is that right?
Here's how it works. For the training data, it will be perfect for the cumulative distribution function, but not for the testing. So here's how it works. You have a model, you have a set of observations, and then you have a set of predictions that match those observations, right? So that's a set of ordered pairs. Then what you're going to do is rearrange all of the observations from smallest to largest. You're going to rearrange all of the predictions from smallest to largest. That forms a cumulative distribution function. So far, so good. Now, for every predicted value, it has a position, an ordinate position, right? So it's like it's the 30th percentile, or in 1,000 samples, 30.042, right? So you go over to the observed CDF and you find that position on the ordinate, and you find the corresponding measured value. So then every predicted value in essence is repositioned. If you plot the corrected predictions against the original observations, you barely see a change. You'll see a shift, but the R squared almost never changes. The bias almost never changes. But the cumulative distribution function under training is now perfect. It has to be perfect because you mapped it to perfect. The testing does not map to perfection, but it comes close. And like I said, it is a method also, it's also a method used in what they call data assimilation. It's kind of it had just not been used in this application before.
Great, thank you.
Sure.
I have one clarification question and maybe follow-up. Were these examples mostly for near surficial alluvial aquifers, or did you have a
Oh,
lot
these
of?
are deep.
Okay.
This is like the Colorado Plateau. A lot of these wells are hundreds of meters deep.
Okay.
In fact, all the public supply wells are, typically 150 to 400.
So you had a lot of bedrock aquifers in this.
Bedrock aquifers, well, in the glacial world, you call them bedrock aquifers because you got this nice superficial material. But you go to the Gulf Coast, for example, there's 10 kilometers of unconsolidated sediment. And the uppermost sediment's no longer used because of superficial contamination. So those wells are typically in semi-consolidated, Cenozoic age materials. So I don't know if you call it bedrock or not.
Okay, I guess my question is, depending on fractured bedrock aquifer and more of a alluvial aquifer, did you see a lot of difference between predictability of your machine learning model?
I didn't look at that, but later I can, because I have it on my laptop.
Cool.
We could.
Yes, is there a question from the chat?
This question is coming from Randall Barnes. They say, have you considered using a prediction of opportunity approach or a forecast of opportunity approach? Some areas are more amenable to prediction than others, this beyond the data density. By fitting over all of this data, hard areas may be damaging the learning for the easier areas.
We have not tried those approaches. As much as I can say about this, I've been a follower. Tom Nolan got us started on this. And Tom, when we began, did what he likes to call a shootout. That's probably not the best terminology in today's day and age, of many different methods. And it included artificial neural networks, it included Bayesian regression, and the random boosted regression was not yet available. The random forest won out hands down. With respect to different areas, one advantage of a decision tree approach, in my estimation, is that those areas that are recalcitrant kind of separate out to different trees. But that the decision tree approach can say, if these data are located in one area, just send them down a different set of trees, and all the other data can go down a different set. So I'm not sure that recalcitrant areas can't be handled in decision trees. And I could say that actually, but based on a really interesting result that's not yet published. We're modeling the thickness of regolith in the Delaware River Basin. And there's a global model of regolith thickness. And the global model performs shockingly well in that area. And part of the reason is that it uses a lot of that data. But also, it's probably the case that the ensemble of all those processes that the global model is forced to accommodate makes up for the fact that this is just a local area. That I get the sense personally that these machine learning models do leverage information from other areas to make estimation. Whether or not that's real requires, additional testing.
Okay, it's 4:30 now, so maybe some of you can stay further to continue the discussion, but the features component, I think we can end here, and let's thank our speaker once more.